In Chapter 7, we're going to be introduced to a new concept. What's interesting, though, is some of the underlying processes we'll go through later on is similar to what we were doing with z-scores and t-distributions. That fundamental basis helps us out in this also as well. But the new thing we want to try to introduce, going beyond what we've done so far, is hypothesis testing. So Section 7.1 is an introduction to this idea. So a hypothesis test is a process that uses sample statistics to test a claim about the value of a population parameter. For example, consider that a manufacturer advertises its new hybrid car has a gas mileage of 50 miles per gallon. However, if we suspect that the mean is not as much as they claim, how could we show that they might be false? A statement about a population parameter is called a statistical hypothesis. In order to complete a hypothesis test, we make a pair of hypotheses. First, we call one the null hypothesis. This hypothesis is the one that represents the claim that's being made. So in the example of a car manufacturer claiming miles per gallon, that would be their null hypothesis. The alternative hypothesis is what's offered in contrast to the null hypothesis. It's the complement. So it's the hypothesis that the null hypothesis is not what it says it is, basically. So in the case of car manufacturers claiming miles per gallon, we would claim the alternative hypothesis if we think they're not telling us what the actual miles per gallon is. When one of the two hypotheses is fake, the other must be true. Either hypothesis, the null hypothesis, or the alternative hypothesis may represent the original claim. In our new notation, we're going to denote the null hypothesis as capital H sub 0. And it's just going to be the statistical hypothesis that contains a statement of equality, such as less than or equal to, or greater than or equal to. The alternative hypothesis, being the complement of the null, will be denoted capital H sub A. It's a statement that must be true if H0 is false, and it contains a statement of strict inequality, such as strictly greater than, not equal to, or strictly less than. The symbol H0 will, sometimes I'm going to say H0, but it's read as H sub 0 or H naught. And HA is sometimes read as H sub A. But I might just say H of A or HA just for convenience sake here. However, in some textbooks you might notice that they, instead of writing H sub A, they write H sub 1. It's the same thing as the alternative hypothesis. It's just some places like to use A for alternative, and other places they use the number 1 for alternative hypothesis. So to write the null and alternative hypothesis, we're going to translate a claim made about the population parameter from a verbal statement into a mathematical statement. Then we're going to write its complement. So for instance, if we have H0 is mu less than k, then H sub A would be mu greater than k. It's the opposite of the null hypothesis. So the null hypothesis has less than or equal to. The alternative hypothesis is the opposite or the complement of the null. We would see that here in the case where you have like the null hypothesis H sub 0 is mu greater than or equal to k. The alternative hypothesis is mu less than k. And in the case of an equation like equals, the null hypothesis mu equal to k would go along with the alternative hypothesis mu not equal to k. And so you may want to look through this at your convenience, at your leisure, if you want to go through some of the terminology that's used. We'll go through several examples translating the verbal statements into the mathematical statements for null and alternative hypothesis. It's useful to give names to the three types of alternative hypothesis. The first form, where it's less than, leads to what we're going to call a left-tailed hypothesis test. It means it requires testing whether the population parameter lies to the left in the lower values of the claimed value. So less than, we'll be using left-tailed to refer to that. Similarly, the greater than form, the second form, leads to what they call right-tailed hypothesis, because it requires testing whether the population parameter lies to the right in the greater than value side of the claimed values. The third form, not equal to, leads to what's called a two-tailed hypothesis test, because it requires testing whether the population parameter lies significantly farther to either side of the claimed value on the left and the right. This tailed terminology, left, right, or two-tailed, also corresponds to the normal distribution curve. If it's a left-tailed test, we're testing if the alternative hypothesis, when it contains the less than inequality symbol, because that's on the left side of the normal distribution curve. The right-tailed test on the greater than direction would be on the right tail of the normal distribution curve. And the two-tailed test, when it's not equal to in the alternative hypothesis, is when you're looking at both left and right tails at the same time. So that's what they call it, two-tailed. Let's go through some examples, some scenarios. We're going to identify the population parameter, state the null and alternative hypothesis, and indicate whether the hypothesis is left, right, or two-tailed. Starting with the first one here that says the manufacturer of a new model of hybrid car advertises the mean fuel consumption is equal to 62 miles per gallon. A consumer group claims that the mean is less than 62 miles per gallon. So what we say here is the mean, mu, is the population parameter for miles per gallon of all the cars that they manufacture. The null hypothesis is what they're advertising, that the mean miles per gallon is 62 mpg. The alternative hypothesis is that the mean mpg is less than the 62 advertised. So in the terminology that we're going to use, we're going to write it like this: denote h sub 0 as mu equal to 62 mpg. Alternative hypothesis h sub a is mu less than 62 mpg. Since the alternative hypothesis is a claim about it being less than, we call it left-tailed. In this other situation, it says the Ohio Department of Health claims that the average stay in Ohio hospitals after childbirth is greater than the national mean of 2 days. So the population parameter would be the mu length, average length of the hospital stay after childbirth in Ohio hospitals. The null hypothesis is what they're saying it to be. The mean stay is the same as the national average, 2 days. So the alternative to this could be that it's greater than 2 days. We could make that claim. We could also make a claim of less than as well, or not equal to, but here it's saying greater than, so more than 2 days. So h sub 0, the null hypothesis, is mu equal to 2 days. But they're offering the alternative to that. The alternative hypothesis, h sub a, is mu greater than 2 days. And since it's greater than, we will refer to this as a right-tailed hypothesis test. Lastly, this one says a wildlife biologist working in Africa savanna claims that the actual proportion of female zebras in the region is different from the accepted proportion of 50%. So notice they use the word proportion. So for population parameter, we're looking at the proportion P of female zebras in the African savanna. The null hypothesis is the accepted proportion of 50-50, or 0.05. But they're claiming that it's not 50%. They don't say greater than, they don't say less than, just that it's not 50. So how we're going to write our null and alternative hypothesis is h0 is p equal to 0.5, and h sub a is p not equal to 0.5. Since it's not equal to, it's what they call a two-tailed hypothesis test. So as we go through a hypothesis test, there will be two possible outcomes. We can either reject the null hypothesis. If we reject the null hypothesis, this is when we have evidence to support the alternative hypothesis. The other possible outcome is we reject, or we do not reject, the null hypothesis. If we don't reject the null hypothesis, we don't have enough evidence to support the alternative hypothesis. Notice that accepting the null hypothesis is not one of the possible outcomes, because we always start with the null hypothesis as a starting assumption. So we're either going to reject it or not reject it, depending on if we have evidence for the alternative hypothesis. So the hypothesis test may give us reason to reject the starting assumption, but it cannot by itself give us reason to conclude that the starting assumption is true ultimately. That's why we're trying to kind of start with something and then work our way to see if we have evidence against it or not against it. So in the long run, how we're going to decide if we have evidence to support the alternative hypothesis is by using the basis of statistical significance. We determine the outcome of a hypothesis test by comparing the actual sample statistic to the results expected if the null hypothesis is true. If the chance of a sample statistic as least as extreme as the observed statistic is less than 1 in 100 or 0.10, then the test is statistically significant at the 0.01 level and offers strong evidence for rejecting the null hypothesis. So if we take a sample and the probability of getting that sample is only 0.01, then we have strong evidence to support that it's because the alternative hypothesis is true, basically. If the chance of a sample statistic at least as extreme as the observed statistic is less than 1 in 20 or 0.05, then the test is statistically significant at the 0.05 level and offers moderate evidence for rejecting the null hypothesis. So what's going to happen is if the chance of a sample statistic as least as extreme as the observed statistic is greater than the chosen level of statistic, so if our significance is greater than 0.05 or 0.01, whichever one is chosen, then we do not reject the null hypothesis. So this is a lot of things to say. Let's try to go through what's going on here. This statistical significance level is either going to be 0.01 or 0.05 for us, for the most part, and results in something we call the p-value. The p-value, which is probability value for a hypothesis test, is a claim about a population parameter is the probability of selecting a sample statistic with at least as extreme as the observed statistic, assuming the null hypothesis is true. Because it's a probability, it'll be between 0 and 1. So what we're going to do is a very small p-value indicates that the sample is unlikely and therefore provides reason to reject the null hypothesis. Basically, since we're starting with the assumption that the null hypothesis is true, then this sample we get contradicts it. And the probability that it happened for some other reason is higher as a result for other than the null hypothesis. It's very unlikely that the null hypothesis being true would result in a sample that comes out like we might see. So the p-value tells us that. A large p-value indicates that the sample result could have easily occurred by chance, so we cannot reject the null hypothesis. The interpretation of p-values can therefore be summarized as follows. We reject the null hypothesis H0 if the p-value is less than or equal to the significance level chosen, such as 0.05 or 0.01. So the smaller the p-value, the more evidence there is to reject the null hypothesis. A very small p-value indicates an unusual event under the assumption of the null hypothesis. Remember, however, that even a very low p-value does not directly constitute proof that the null hypothesis is false, only that it is probably false. We're speaking in terms of probabilities here, not 100% likelihood. Just small or very high confidence levels, let's say. So let's look at an example here. It says you perform a hypothesis test for the following claim. Should you interpret your decision? How should we interpret the decision to reject the null hypothesis? Or if we fail to reject the null hypothesis? The claim here, which is the null hypothesis H sub 0, is a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. So this claim is represented by the null hypothesis H0, and if we reject the null hypothesis, we should conclude that there is enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. If we fail to reject the null hypothesis, we would conclude there is not enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. The evidence that we use to support our reject or not reject the null hypothesis will be according to that mentioned p-value. The smaller the p-value, the more likely we have the evidence to reject the null hypothesis. So to summarize it here, we're going to state our null and alternative hypothesis down, H0 and H sub A, mathematically using greater than, less than, greater than, equal to, and so forth. We're going to specify a level of significance. Some cases we'll use a letter alpha to stand for level of significance. Then we're going to determine the standard sampling distribution and draw its graph, and then calculate the test statistic and its standardized value. What this means is, like most of the time, it's going to be normal distributions for what we're going to do here. We're going to find the p-value, and then we're going to base our decision on the p-value. If the p-value is less than or equal to the level of significance, then we reject the null hypothesis. If the p-value is not less than or equal to the level of significance, then we fail to reject the null hypothesis. We'll write our statement to interpret the decision of what we're claiming here. Let's look at this example here. It says a car leasing firm's records indicate that the mean number of miles driven annually in its cars has been about 17,750 miles. However, they suspect that this number has decreased in the past year. To test this claim, we're going to suppose the firm wishes to choose a small sample of driving distances from the past year and carry out an hypothesis test for its suspicion. Let's state the null hypothesis and the alternative hypothesis in this situation here. And then, once we know what the null and alternative hypothesis should look like, let's consider if they draw a sample, and then find the significance of drawing the sample to be about 0.03, which is what we're going to call the p-value. And we're going to talk about the level of significance at 0.05. Would we reject or not reject the null hypothesis? So with that in mind, let's write down the null and alternative hypothesis. The null hypothesis is the starting assumption. So we're going to start from the basis that they're claiming that the average miles driven is 17,750. So H sub 0 is mu is equal to 17,750 miles. They want to test the claim, though, that it's gone down from this average here. So the alternative hypothesis H sub A would be the mu is less than 17,750 miles. Now we'll talk more about the sampling and p-values and how we get this in a little bit, but let's say that the p-value for the significance of a sample is 0.03 in this case. So they take a sample and they find their significance level and all that stuff. So based off of that, do we have evidence to reject or not reject the null hypothesis? It's all based on if the p-value is less than the level of significance. In this case, since the 0.03 is less than 0.05, the p-value is less than significance level, and we can reject the null hypothesis at the 0.05 level. And if we reject the null hypothesis, we then again have evidence to support the alternative hypothesis, their claim that the mileage has declined. On the other hand, it doesn't say anything about the 0.01 level, but there are cases where we compare to 0.01 instead of 0.05. In that case, it would not be significant at the 0.01 level, and we could not reject the null hypothesis. So it really just depends on how low of a significance level a particular study wants to go. The lower you go, the harder it is to get evidence to reject the null hypothesis. So to summarize the last few slides in this section, the null hypothesis is the starting claim or assumption. We state the alternative hypothesis as the opposite or complement to the null hypothesis. And then we're going to seek if enough evidence supports the alternative hypothesis and gives enough support to reject the null hypothesis. The p-value will be the probability that a sample could be drawn under the assumptions of the null hypothesis. However, if the p-value is low, then it's less likely that we could have drawn that sample if the null hypothesis is true. As a result, if the p-value is below the level of significance, then it means we have enough evidence to reject the null hypothesis and support the alternative hypothesis.